complex analysis. Today we're going to start the exciting study of integration where we have complex valued functions. Now before we can really get started here, I want to review the theory of the integration of real functions. I know that you've seen it in your calculus classes, but you may not have seen its rigorous development. And so what we're going to do here is we're going to do a parallel development of integration theory in the complex case, but also integration theory in the real case, culminating with the fundamental theorem of calculus in the complex case, but it will have a specialized version which applies to the real case. So we need to start with basic definitions. So the core concept of the integral is the concept of the area. The notion of the real integral is the integral from a to b of f of x dx represents the area underneath the graph above the x-axis between a and b. So you might take this to be your, why not take that to be the basic definition of the integral? That's what it is. It's the area. If you want to calculate the area, then you estimate it by Riemann sums or something. Why can't that be our basic definition of the integral? The problem with that is that requires a remarkably sophisticated and well-developed geometry so that we can talk about the area not only of circular sections and triangles and rectangles and trapezoids and whatnot, but also of strange arcs and things given only by formulas. So we don't really have a well-developed theory of geometry, at least not pre-calculus theory of geometry, that can handle this very, very rich concept of area. And so instead of defining the integral to be the area and presuming that there's already some rich concept of an area lurking in the background, we're going to define the integral to be the, well, on the basis of the Riemann sums. And then we're going to calculate that, we're going to treat that as an estimate to the area that gets better and better when we take the limit. So let's take a look at how this works. Preliminary definition of the integral is the integral from a to b of f of x dx is going to be this summation. This summation is a Riemann sum, and it might look a little different from the formulas that you've seen, but it's basically the same thing. This is what we treat as delta x. This is often called delta x here, the difference between some endpoints. And f of tau I is going to be the function value at some point. Now, here I'm breaking up the integral into n sections. I think I want to make this m for now. M sections, so I goes from 1 to m, and then I'm assuming that we have some sort of division here. These ti points are dividing points, which begin at t0 equals a and continue in a division across here, t3, t4, t5, T6, and B is going to be T7 in this example. And so we assume that we have some division. The data of this division is called a partition, although we will add a little bit more information to the partition shortly. So this divides the region from A to B into 7 equal pieces in this case. And then these taus are not t's, right? These taus are, we're going to call them sample points. So here, let's give some vocabulary to this. With endpoints, t sub I, and sample points, tau sub I. Now, the rule for the sample points is that they have to be in between the endpoints. So in other words, tau 1 has to be somewhere between t0 and t1. It has to be somewhere in here. It could be t1. If it is, then we're using the right-hand rule. It could be t0. If it is, then we're using the left-hand rule. It could be the midpoint between them, in which case we're using the midpoint rule. But somewhere in each one of these smaller rectangles, there is a value tau, an x value in between the two endpoints of that rectangle, and we sample there. So I'm not even assuming that the rule for choosing the taus is necessarily consistent from one rectangle to the next. So this one might use the right-hand rule, and this one might use the left-hand rule, and those two tau values might actually be the same value. But I am assuming that the tau value has to be in between the appropriate t values. And so what this means in inequalities is that tau I has to be between ti and ti minus 1. And of course, the ti's have to go in order. So a less than or equal to t0, less than equal to t0, less than t1, less than, etc. And then we end with tm, which must be b. So basically, we get all of this division data, and then that allows us to calculate the Riemann sum. F of tau I is a height estimate for this rectangle, and we are multiplying for each rectangle this height value times this width in order to get the area of a rectangle, and we're approximating the area of the curve as the area, the sum of the areas of the rectangles. Now, I say we're approximating. This summation calculates the sum total of the areas of the rectangles. It does not exactly calculate the area, and so this equals is not quite right here. First of all, it's an equals by definition, so let me make it a triple equal. But because this is not exactly equal to this, this only gets closer and closer to this as these rectangles get smaller and smaller. And so I mean smaller and smaller in width, of course. And so the integral is actually a limit here. And so now we have this important question. What kind of limit are we dealing with here? And that's actually a really subtle question. It seems like it's a simple question. So what sort of limit is this? So the first answer, and sort of the most basic answer, and often the answer that's given in a standard Calc 1 or Calc 2 course, is that the limit is as m goes to infinity. And so that's not a bad answer, but I want to provide some criticisms for it. So as m goes to infinity, and then ti minus 1, this width, must then be regarded as a function of m. So if so, then this will have to be equal to b minus a over m. And that means that ti itself must always be equal to a plus b minus a over m times I. So we get a convenient formula for ti itself. Now we don't actually have a formula for tau I here, and that might cause you some concern here. But you could make a rule for tau I that it's always equal to ti, for example, and then this would be the right-hand rule. So this is one option. I want to critique this option. I want to give you a few reasons why this might not be the very best policy. So I'm going to critique the proposal that this limit is interpreted as the limit as m goes to infinity. And again, this is a preliminary definition. It needs some work. So why shouldn't we simply interpret this as a limit as m goes to infinity? So this forces the rectangles to all be the same width. Now, that doesn't immediately seem like a problem. Why not force all the rectangles to be the same width? Well, because a few problems are much easier to calculate if we allow the rectangles to have unequal widths. So often unequal widths, well, maybe not often, but at least sometimes, sometimes unequal widths are more convenient. In other words, we can calculate more easily. And the example that I'm thinking of is if we do, for example, the integral from 1 to b of 1 over x dx, which should be log b, this is best estimated with unequal widths. And a little exercise for you to check on your own time is if we set ti to be equal to b to the, what's the power, m over I, then all the rectangles have the same area. So that's a very strategic choice if you're trying to calculate this integral. If you manage to prove that all the rectangles have the same area, then calculating the Riemann sum integral is really just a question of counting how many rectangles there are. And so that's nice. Actually, I'm being a little bit imprecise here because I haven't told you what the tau i's are. But you can just use the right-hand rule, set tau I equal to ti, and then this will be true, that they all have the same area here. So there are some cases when we would like to have unequal widths so that we can have convenience in calculation later. But more importantly, so this is my first objection to simply regarding this as a function of m. But the second objection is it causes a strange phenomenon. It causes the integral to only depend on the rational values of x. So, but this causes the integral from a to b of f of x dx to depend entirely on rational x. And this is sort of theoretically wrong. Let me explain why I'm claiming this first, and then explain why it's a problem. So on x in the rational numbers. So why am I claiming that it depends only on rational x? Well, assuming that a and b are rational, if we end up with, which is part of a hidden assumption of this claim, if a and b are both rational, then this is a rational number, and this is a rational number, and I is an integer. And so ti will always be a rational number in this calculation. And if we also use the right-hand rule, say, and set tau I to be ti, or set tau I to be the midpoint between them, which would be the midpoint rule, or ti minus 1, which would be the left-hand rule, if we make any of those policies, then all of the tau i's are rational values, and this depends only on the values of the function at rational inputs. And so all of the irrational inputs to f are irrelevant. Now, as you know from set theory, there are countably many rational numbers and uncountably many irrational numbers in the interval from a to b. And so it seems a little bit theoretically wrong that the relatively few, the countably many rational numbers between a and b would be in charge of determining the integral of f of x between a and b. It seems like, you know, too few are counting as too important there. And if you've taken any higher measure theory, then you know that the rationals have measure 0, and in fact, the values of the functions along the values of the function along the rationals shouldn't matter very much at all to the integral of the function on this interval. And so this feels theoretically wrong, that it causes the integral to depend only on the rational values. And so what we need to do here is we need to refine what this limit is really depending upon. And so how are we going to do that? Instead of taking the limit to be a function of m entirely, we're going to be regarding the limit to be a function of a partition. And so we're going to call that partition P. And the partition is merely a record of all of the dividing points ti and all of the sample points tau I meeting these conditions. And then we're going to regard the Riemann sum to be a function of a partition, and then we're going to define that limit as something happening to the partition. So let's first define a partition, and then we'll define the Riemann sum in terms of it. So a definition of a partition of an interval AB is a sequence ti with, so ti, I should say, where I goes from 0 to m, with 0 equals, no, not 0, a equals t0, which is less than t1, which is less than tm, which is b. Okay, so it's just this division into these things. Now, notice that the sample points tau I are missing. That's because I'm going to make that a sort of an extra bit of information, and we're going to call that a tagged partition. So a tagged partition, oops, I spelled it wrong. So a tagged partition, P, I'm going to use the same notation for a partition and for a tagged partition, so hopefully that won't cause confusion. So is a partition, I keep dropping part of this word, is a partition together with sample points tau I, and again, I here ranges from 1 to m, and the idea is that the tau I is going to lie between the ti and the ti minus 1, just as happened in this. So basically what we're doing is we're abstracting the data about how this interval gets divided. That's a different kind of data from the actual process of producing the Riemann sum. So the division of this interval a to b is divided in a certain way, and you could use that for a Riemann sum for one function. You could use the same division for a Riemann sum for a different function. That's sort of getting separated from the question of how we calculate the integral or the Riemann sum. It's just the question of how do we divide an interval and set up some sample points within each of those things. So that's what a tagged partition is. Now, I want to caution you with the notation here. As we move forward, we will deal with a lot of partitions, and we will call almost all of them P. The division points we will always call T, T0, T1 through Tm, or N. The sample points we will call tau. At a certain point, things will get complicated, and we'll have to talk about the relationship between various partitions. If we have another partition, we might call it Q. We might have a different collection of division points, and we might call them S's. And then in that case, we would have a different collection of sample points, and we would usually call those sigmas. So we try to be a little bit consistent with the notation here. So now, on the basis of a partition, we can produce this summation here. And this summation can be thought of as a function of the partition. And so, so the Riemann sum here can be thought of as a function of the partition. And then this limit can be interpreted as doing something to the partition itself. So now, this is still preliminary because it still doesn't explain exactly what the notion of that limit is. So preliminary definition 2, again, second preliminary definition for real value functions, and I haven't gotten to complex value functions, but I promise we will get there. So the preliminary definition number 2 is that the integral from a to b of f of x dx is the limit of the summation of f of tau I, and then ti minus 1. This goes I equals 1 to m. Now, all of this is thought, we can think of this as a function of f, but it's really a function of the taus and the t's, so it's all a function of a partition. So in the background here, I'm thinking of all of this data, the t's and the taus, as coming from some partition P. And then we're going to take the limit as P goes to 0. Problem is, that doesn't make any sense. P goes to 0 doesn't make any sense because P is not a number. So something has to go to 0. And it has to mean that this partition is getting finer and finer and finer. And so what we're going to do is we're going to call this the norm of the partition. And we're going to use double absolute value signs for that. We're going to say the norm of the partition goes to 0. And now we're closer to making a sensible definition here. There are two problems with this definition, which is the reason why it's still preliminary. The first problem is I haven't given an official definition of the norm of the partition. That's an easy solve. The second problem is this is now a new kind of limit, right? This limit is not the limit as, it's not a limit in a metric space, at least not in any obvious way. It's not a limit of a sequence, not in any obvious way. So this is a new kind of limit, and it needs its own kind of definition. So there are two ways that this definition is incomplete. This is now the right definition, but I need to explain what I mean by the norm of a partition, and I need to explain what I mean by this funny limit. So the first of those is easy. Let's do that easily. So, so where the norm of the partition is equal to the norm. Now, if the partition doesn't have equal widths, then I can't just say it's the width of every rectangle. So what I really want here is I want all of the rectangles to get small, right? I don't just want some of them to get small and some of them to remain large. I want all of the rectangles to remain small. So if that's going to be measured by the norm, then the norm should be the maximal width of those, so that when the norm goes to 0, they all have to get small. So the norm of the partition is going to be the maximal width. Now that maximum, I'm saying maximum, I don't have to say supremum because there are finitely many rectangle widths involved here. There are only finitely many, so I can simply take the max. So this is going to be the maximum over all I, and the I here will go from 1 to m. So it's the maximum of all the i's in that range of the widths. So that's ti minus ti plus 1, I minus 1, previous. Notice that this has to be a positive number because of these conditions here. And so there are finitely many positive numbers, and so there's a maximum. So that's how we measure the norm of the partition. If the norm goes to 0, that means the maximum width goes to 0. That means they all become narrow, which is what we want if we're actually using these as approximators to an interval. So that's problem 1 solved. What does this norm of a partition mean? But problem 2 is deeper. This introduces a new kind of limit. And we need to give an accounting for what this kind of limit really means. And so what we're going to do is instead of, different authors and different lecturers treat this differently. Some people will give you an account for what this limit means as a Riemann sum specifically. But I want to give a little bit more generality than that. I want to think of this as just any function of a partition, no matter whether it's a Riemann sum or something else, just something that depends on a partition. I want to give an account for what this limit as the partition norm goes to 0 of any function of a partition, what that would mean. And so let's give a definition of that. So now I want to assume that we have a function of a partition, and we're going to call this function phi, thinking of it as a generic function. But of course, in the back of your mind, think of this as phi of p. This really is a function of a partition because it depends on the partition's data, ti's and tau's. So let's give a definition of a limit of phi of p as the partition norm goes to 0. So, definition. And this is partition limit definition. So let's let phi be a function from the set of all partitions of A, B. So its input, one partition will be an input to phi. So the domain of phi is the set of all partitions of A, B. And the codomain is, well, this gives us a real number out, right? So this, for a fixed function f, this will take a partition in and give us a real number out. And so I could say reals here, but I know eventually that I'm going to want to generalize this to the complexes, and so I'll put complexes there. And if it does happen to just map to the reals, well, no worries, because that's a subset of the complexes, so that will be included in this case. So we have a function from partitions here into some complex space. I could actually do this into any metric space, and that would work just as well, but there's no need for that generality here. The limit, so lim as partition norm goes to 0 of phi of p is defined to be that value L, if it exists, of course, so that now what we need to say here is, if you want to get this value phi of p close to L, then you can by choosing this sufficiently small. So for every epsilon greater than 0, that is how close to L you want to get, there exists a delta greater than 0, that is how small the norm has to be, so that for every p, and I'm not going to quantify this, like that is for every partition of AB, for every partition there is. So if the norm of the partition is indeed less than delta, then the distance between phi of p and L is indeed less than epsilon. So this is, I mean, if you had to make up a limit definition for this, this is probably what you would make up. If instead of the complexes here, I want an arbitrary metric space here, then I just have to replace this with the distance function between phi of p and the element L. This basically says, if you want phi of p to be close enough to L, you may get phi of p as close to L as you want by choosing phi having a sufficiently small norm, and then it will be close to L. So this is what that limit then means. And this gives us a full accounting of what the real integral is. Now, that tells us what the real integral is. The next thing that we want to do here is we want to generalize this to the complex numbers, and we want to give an account for what a complex integral is. And that's actually really difficult to do. So it's not clear what should change when we generalize from the real case to the complex case. And so this is going to take some real exploring. So we're going to start this in the next video.